This is Kundana. In the last sessions, we discussed about water technology. What is hardness? What are the different types of hardness? And what are boiler troubles? And how to remove hardness. In that, we discussed about internal treatment, external treatment. So, internal treatment, we have colloidal conditioning, phosphate conditioning, and carbon conditioning. And in external treatment, we have so many methods, but we discussed about ion exchange method. In today's session, we are going to discuss about the next type of treatment, that is zeolite method in detail. And apart from that, we are also going to discuss about the problems related to hardness calculation. Come on to the topic. So in this session, we are going to discuss about your zeolite method. So zeolite. So what do you mean by zeolite? So we know that how the purification started means purification started initially by using tripart method. This tripart method changes to candles, filter candles like Ganga water filter like that, and later it changes to your RO. That is, you are using right now. We are using Kent, Aquaguard, Pureit like that, where it consists of your resins chambers. So in that we are using the different types of ion exchange resins only. But in between this ion exchange method and your water filters, we have one more technology where single chamber is used for purification. So right now in in water bubbles, so where the people are supplying water to all the houses, in that where in that condition you are going to observe this zeolite process. This zeolite chamber consists of only a single chamber. In zeolite method, we have only a single chamber. It consists of a single chamber. Whereas in ion exchange method, we have two different chambers. So this is your zeolite chamber. And this zeolite chamber itself consists of your partitions. Okay. The first chamber, the first most chamber consists of your brine solution. It consists of brine solution, nothing but NaCl. It is known as your 10% NaCl, which is known as brine solution, which is known as your brine solution. And this brine solution is having a tap-like structure for its removal. Whenever it is essential, it will be loosened, then automatically the brine solution will enter. Okay, and it consists of an inlet. It consists of an inlet to have raw water. So through this inlet only, we are going to send raw water. The water where we are going to remove your hardness, that water is sent through this inlet. So this inlet is having, beyond this inlet we are having the layers, that is your pre-filters. These are known as your pre-filters. This is your pre-filter. What is the use of this pre-filter means? To remove the suspended impurities. To remove suspended impurities. Suspended impurities. We are having the pre-filters. And next to it we have the zeolite bed. So this is your zeolite bed. Zeolite bed. This is zeolite bed. That means the complete hardness causing salts are removed in this zeolite bed only. This is your zeolite bed, which is represented like this. So it is your zeolite bed. Zeolite bed. And next to it, it has more space here. We will take this one with the more space. So this is your empty spaces where we are going to collect, and here we have an outlet to collect soft water, and one more outlet is at the bottom to collect washings, and here we have the purified water. It is your purified water. Purified water. Okay. So this is about your geolite method. So in the geolite method, what does it consist of? It consists of only a single chamber. The single chamber is having different layers. The first layer is your brine solution, and next to it has an inlet to send the raw water. Next to it has a pre-filters to remove the suspended impurities, and later it has the geolite bed for purification purpose. And next it has the layer to collect the softened water, and at the bottom we have the suspended impure suspended layer which is having a gravel layer to remove the waste particles to allow the waste particles to pass through it. And it has an two outlets. One outlet is to collect soft water and the other outlet is to collect your washings. Now move on to the process. What is the process happening? Before that, let me explain you what you mean by a geolite. Zeolite is known as your cation exchanger. It is known as cation exchanger. Very, very important for your objective questions or in the fill in the blanks also. Zeolite means it is nothing but Ne2O Al2O3 X SiO2 dot YH2O. That means sodium aluminosilicate. It is known as hydrated. It is known as hydrated sodium aluminosilicate. Sodium aluminosilicate is known as your geolite. So what is the chemical composition of your geolite? Geolite is nothing but your hydrated sodium aluminosilicate. And geolite acts as cation exchanger. Why it is known as cation exchanger, that we will go through when we are moving to your process. Okay. And coming to the classification, this geolite is classified into two types. It is categorized into two types. One is natural geolite. One is natural geolite and the second one is artificial geolite. Natural geolite, artificial geolite. What do you mean by this natural geolite? Natural geolite means nothing but the geolites which are readily available in the nature. That means these are not prepared by us. It is already existing in the nature. Those are known as your natural geolite, and the best example is your natrolite. Natrolite is the best example. Next one is your artificial geolite. So that means we are preparing by using the chemicals. So those are known as your artificial geolite. The best example is your China clay and feldspar. These are the two examples for your artificial geolite. So geolite is a cation exchanger. The chemical composition is hydrated sodium aluminosilicate. These are of two types. One is natural and other one is your artificial. The natural one is natrolite. Artificial one is your China clay and feldspar. Now move on to the process. What's the process happening here? First, whenever raw water is sent into your geolite chamber, what is happening here? The filtration takes place. Later, what is happening? The geolite is removing the all cations hardness causing salt. How it is happening? Let us see. So, the geolite can be represented by the formula Na2Ze. Na2Ze means nothing but your high Na2O Al2O3 X SiO2 dot H2O. So hydrated sodium aluminosilicate is known as your geolite and it is represented by the formula Na2Ze. Okay. Now the reactions are happening inside the chamber. So for that reactions we are representing the complete formula as Na2Ze. Okay. Now move on to the reactions. What is happening here? Now water consists of your calcium chloride, calcium sulfate, calcium carbonate, calcium bicarbonate. It also consists of magnesium chloride, magnesium sulfate, magnesium carbonate, magnesium bicarbonate. It consists of all these salts. Whenever the water is passing through this chamber, what is happening here? So here the geolite is reacting with your hardness causing salt. Then what is happening here? Just have a look. So we are taking Na2Zd, Na2Zd when it is reacting with calcium chloride. Now it is now water consists of this all these salts I already told you. When it is reacting with calcium chloride, what is happening here? Just have a look. So what is the cation here? Calcium. So what is the cation in the zeolite? Sodium. So this sodium get exchanged by your calcium. Because of that reason only it is known as your cation exchanger. So now what we will get? You will get this one as Ca2Ze plus 2NaCl. Okay. So now what is happening here? Here you are getting your CaZe. So you are getting it as CaZe plus NaCl. You are getting it as CaZe plus NaCl. When it is reacting with CaSO4, then what will happen? Again you are getting CaZe plus Na2SO4. When it is reacting with calcium bicarbonate, then you are going again CaZe plus NaHCO3 twice. That means these are the reactions. Suppose it is reacting with your carbonates, then also same. We are going to get Na2CO3. When it is reacting with CaCO3, you will get CaZe plus Na2CO3. Similarly, with your magnesium also, the same thing will happen. Instead of calcium, you will get it as magnesium zeolite plus your NaCl. And if it is reacting with magnesium sulfate, then again it is same. Magnesium zeolite plus Na2SO4. That means, what does it mean? All cations are getting replaced by your sodium. Because of that reason, what is happening here? All your calcium and magnesium are removed. Okay, removed from your water. Now water consists of only your anions, that is your chlorides, sulfates, carbonates and bicarbonates, which are not at all responsible for your hardness. If it is mixed with your calcium and magnesium, then only it is responsible for hardness. If it is alone, it won't cause any hardness. Okay. So now water consists of your sodium chloride, sodium sulfate, sodium bicarbonate, sodium carbonate, like that, which are not responsible for your hardness. Because of that reason, what is happening here? The residual hardness of your zeolite is only 10 ppm, which is very less and which is suitable for consumption purpose. Okay. So after few cycles, after using few cycles, after using multiple times, what will happen? The zeolite gets exhausted. So this is your zeolite bed. Actually, initially it is your zeolite bed, which is a pure form. But after passing through your water, after passing water through it, what will happen? The zeolite bed get exhausted like your tea filtration sieve. So when we filter tea, for number of times what will happen? The filter will get totally exhausted and it won't undergo any filtration. Similarly, the zeolite bed also gets exhausted. That means our pores are completely closed. Because of that, there is no further filtration. Then how to use that one? We can regenerate. How to regenerate means, when this zeolite bed is treated with brine solution, so NaCl, I already told you while explaining the figure. So if you observe the first chamber, if you observe the first part of your chamber, it consists of 10% brine solution. Here what? So now it's time to discuss this. Whenever the zeolite gets exhausted, we are losing this tap. When this tap is closed, what will happen? The brine solution enter into your zeolite bed. Whenever the brine solution enter into the zeolite bed, what is happening? It undergoes regeneration. How the regeneration is happening means, so we are sending your NaCl. Now the zeolite is having calcium zeolite or magnesium zeolite. Then what is happening here? This NaCl gets reacted. Because of that, we are going to get your 2NaCl now. So Na2Ze plus CaCl2. And here also we will get Na2Ze plus MgCl2. That means our zeolite is back. So that means it is ready for further filtration. But if you observe the benefits of this one, if you observe the benefits of zeolite method is the residual hardness is only 10 ppm and it is suitable for consumption also. But what is the drawback of this zeolite bed means? Zeolite method drawbacks, if you consider, it needs skilled assistance. That means a well-known person only can handle this zeolite chamber. A layman can't handle. So if they don't know how, when the bed is getting exhausted and how to regenerate, it is very tough to handle. Okay, because of that reason, only skilled person can use this one, and it is expensive. It is expensive. So this is about your zeolite method. So zeolite is a cation exchanger. Sodium, hydrated sodium aluminosilicate is known as the zeolite. It is two types, natural and artificial. So natural is your naturalite and artificial is your feldspar china clay. And if you send the raw water into the zeolite bed, the water is passing through your zeolite chamber, zeolite bed, then all your cations are getting exchanged by your sodium. Because of that reason, it is known as your cation exchanger. And whenever it is used for multiple times, if the zeolite gets exhausted, after exhausting, what will happen? It won't be undergo purification. So because of that reason, we want to regenerate. How to regenerate means by using your brine solution. When brine solution is passed, what will happen? All your calcium zeolite and magnesium zeolite gets replaced by your sodium, due to which the zeolite is back and it can be used for further purification purpose. And if you observe the benefits, the benefit is the residual hardness is only 10 ppm, which is very suitable for consumption purpose. And if you go with the drawbacks, what is the main drawback here means? They need skilled assistance and it is very expensive. This is about your zeolite process. Now move on to the problems. Hardness problems, which are very important for exam point of view. Without this problem, there won't be any question paper. 90% you can expect problems from this chapter. So before going to explain this problems, let me clarify one thing here, which we discussed already. So we know that hardness is expressed in terms of ppm. 1 ppm is equal to 10 milligram per liter. Sorry, 1 ppm is equal to 1 milligram per liter. 1 milligram per liter, which is equal to 0.07 degree French, which is equal to 0.1 degree Clark. So this we already discussed in the very first class itself only. And we also discussed it that hardness causing salt can be expressed in terms of calcium carbonate equivalents. How to, that is calcium, suppose let us consider 9.5 mgCl, 9.5 mgCl2, it should be expressed in terms of CaCO3. How it can be done? Mean, weight of the substance, weight of the substance by molecular weight of the salt, molecular weight of the salt into 100. So what does it mean? Weight of the substance means 9.5. Molecular weight of the salt means weight of this MgCl2, and 100 is nothing but the molecular weight of your CaCO3. Are you getting my point, Nana? So here 9.5 is the weight of the substance that is given in your problem. Molecular weight is nothing but which we can be calculated using the atomic weights. And this into 100 means as we are converting each and every salt into calcium carbonate equivalents, it is taken as 100. Now how it can be converted means 9.5 is the weight of the substance and molecular weight of the salt is 95 into 100. That means the value is 10 ppm. So that means each and every salt should be converted into calcium carbonate equivalents in this way. Now we go with the problem. So we'll discuss one problem here. This is one. Now we will discuss one problem related to this calculation, as it is very important for exam point of view. Okay. So what is the problem means? Calculate. We'll go with the next page. It will be better. This place is not sufficient. Calculate temporary, permanent hardness. Temporary permanent hardness in degree French of water. Degree French of water sample collected from Nalgonda district, which is collected from Nalgonda district, and it consists of following salts. So first one, the salt is calcium bicarbonate, which is 16.3 milligrams. Next one, magnesium bicarbonate, which is 14.6 milligrams. Next, calcium sulfate, 13.6 milligrams. Next, magnesium sulfate, 12 milligrams. Next, magnesium chloride, 9.5 milligrams. Okay, this is your problem. What is our first step? We need to convert each and every hardness causing salt into calcium carbonate equivalents. Now, what will happen? So, you will get this one as 16.3 by 163 into 100. So, 163 is the molecular weight. Next, 14.6 by 146 into 100. Next, 13.6 by 136 into 100. Next, 12 by 120 into 100. Next, 9.5 by 95 into 100. Now we will get this one as 10 ppm. This is also 10 ppm. This one also 10 ppm. Next, this is also 10 ppm. Next, 10 ppm. All are 10 only. Okay. And before going to calculate here, we need to check each and every salt is responsible for your hardness or not. So, these two are responsible for your temporary hardness and these three are responsible for your permanent hardness. But what is our question? We need to calculate temporary permanent hardness in terms of degree French. So, now temporary hardness. How can we calculate temporary hardness? 10 plus 10. How much? It is your 20 ppm. But what is our question? We need to calculate in terms of degree French. That means 20 into 0.1. So, you will get it as 2 degree French. Next one. So, permanent hardness. How will we get your permanent? 10 plus 10 plus 10. It is your 30 ppm. Now, 30 into 0.1, that is 3 degree French. Then what is the total hardness? Total is equal to 2 plus 3, that is 5 degree French. So that means we need to check whether the given salts are responsible for temporary or permanent. Next, we need to calculate temporary and permanent and we need to convert. So in which units they are asking. So this is your one model. Okay. Next, move on to the second model. So in the second problem, see, calculate temporary, permanent hardness of water Calculate temporary permanent hardness of water containing following impurities. Permanent hardness of water containing following impurities. So what is the impurities we have? Magnesium sulfate 60 ppm. Next, calcium chloride 11.1 ppm. Next, calcium bicarbonate 32.4 ppm. Magnesium bicarbonate 73 ppm. Next, NaCl 36.5. Turbidity 10 ppm. So this is our question. We need to calculate temporary and permanent hardness. That's it. Very simple. And we need to calculate it for 100 ml. For 100 liters of water. For 100 liters of water. This is for 1 liter. So we already discussed that. What we already discussed it here? 1 ppm is equal to 1 ppm is equal to 1 milligram per liter. 1 milligram per liter here. But we need to calculate it for 100 liters. Okay. So first, what is our first step? We need to check whether the given salts are responsible for hardness or not. Okay. So yes. So magnesium sulfate. So it is responsible for which hardness? Permanent hardness. Calcium carbonate, magnesium carbonate, temporary hardness. What about the salt and turbidity, NaCl and turbidity? No, they are not at all responsible for your hardness. They just want to confuse you. So maximum what we will think NaCl means salt. Yes, it is responsible for your hardness. It is your common sense. But this salt that we are consuming are not responsible for your hardness. That salt is differ, this salt is differ. Okay, so this NaCl is not at all responsible for your hardness. Turbidity. Turbidity is also not at all responsible. What do you mean by turbidity? When we add a spoon of milk to your glass of water, what will happen? Automatically the color of the water will change. When we add starch, then automatically the color changes with some colloidal particles. That nature is known as your turbidity nature. The turbidity nature is given here, which is not at all responsible for your hardness. They just want to confuse you. Don't consider sodium chloride and turbidity for your calculation. Okay. Now, what about this one? For 60 ppm, how much it will get? You will get this one as 60 by 120. 60 by 120 into 100. So you will get this value as 50 ppm. Here 11.1 by 111 into 100. You will get this value as 10 ppm. Next 32.4 by 162 into 100. So you will get this one as 20 ppm. Next 73 by 146 into 100. So you will get this one as 5 ppm. Okay, now what is the value of permanent? Permanent is 50 plus 10, that is 60 ppm, and temporary is 20 plus 5, which is 25 ppm. That means it is for 1 liter, but we need to calculate it for 100 liters. So we need to multiply. So then what will happen? Into 100, you will get this one as for 100 liters. For 100 liters, permanent is equal to 60 into 100. You will get this one as 6000 milligram per 100 liter, and temporary as 25 into 100. You will get this value as 2500 milligram per 100 liter. This is your second model. Okay, in the first model, units conversion. In the second model, if volume is increased, then how to calculate the hardness causing salt. Okay, and the last topic, That is your fluorine, defluoridation. Defluoridation. So till now we discussed what is hardness, how to remove your temporary hardness, what are the different methods we have, and how to determine hardness. Also we discussed that. Now we are going to discuss the last topic of our syllabus, that is your defluoridation. So what do you mean by this defluoridation? Before explaining this topic, let me clarify you. Fluorine is the seventh group element. Okay. And this is highly reactive. It can easily attract the electrons from the other groups. Okay. And it is having high electron affinity towards the other elements, due to which it can easily gain the electron. Okay. So why we are going to discuss this defluoridation means, this fluorine is causing some problem not only for animals, it is also causing problem to the human beings also. Especially this fluorine problem is maximum in Nalgonda area. Because of that reason only, uh, total samples they are collected from the Nalgonda area, and they have determined the presence of fluorine in the water and what are the problems faced by the Nalgonda people. Because of that reason only, the technique that is used to remove fluorine from the water is known as your Nalgonda technique. Okay, so defluoridation. So what do you mean by this defluoridation? Means the process of removal of fluorine from the water is known as defluoridation. So process of removal of fluorine. Process of removal of fluorine from water is known as defluoridation. Okay. Here, for the removal of fluorine, there are different methods. We have ion exchange method. We have reverse osmosis method, that is RO. Reverse osmosis method and absorption method. Next one is chemical treatment. So these are the various methods we have to remove your fluorine. Okay. Next, if fluorine is present in water, what will happen? So we are going to observe in some areas, especially we are going to observe bow legs like this. The legs will be in the bow shape, and the tooth of the person is yellow in color. Why this thing is happening means, it is because of your fluorine only. So due to excess of fluorine, what will happen means, due to excess of fluorine, there is a problem of dental cavities. And there is a problem with the skeletal tissues. Where you are going to have bow-shaped legs, and tooth will turn into yellow colored teeth. Yellow colored teeth will be there. Okay. If fluorine is present at the very negligible amount, then also it will be danger. It will cause a tooth problem. Okay. That means adequate amount of fluorine is essential to protect our teeth. If fluorine is in excess amount, then it will cause us these many problems. If fluorine is in minimal amount, then also it will cause us the tooth problem. That means it will require nearly 0.5 to 1 milligram of fluorine. This is the adequate range of fluorine. Okay, but in some areas the fluorine is very high amount, really touches to 10 milligrams also. So to overcome that problem, we need to go with the defluoridation process. At that moment, so this research lab, that is your National Environment Engineering Research Institute. Engineering Research Institute, which is located at Nagpur, developed a technique, known as mud ball technique to remove this fluorine. And this technique was started in the area Nalgonda of Telangana. Because of that reason, this mud ball technique is also known as Nalgonda technique. It is also known as Nalgonda technique. So what do you mean by this Nalgonda technique means? Here, this Nalgonda technique consists of a simple, it's very simple chemicals. So it consists of lime and alum. So what are the chemicals that we are using is, we are using only lime and alum. So first one, flash. First step is flash. Second one, rapid mix. And the next one is flocculation. Next one, sedimentation. Next one, filtration. Next one, distribution to household. So here very simple here. So first one is your flash. So in the flash, what we are going to use? We are going to use lime plus alum. So we are using lime and alum to the water. After adding this lime and alum, we are mixing by using stirrers. We are mixing all this lime and alum to your water by using stirrers. Then after stirring, what will happen? Your fluorine gets converted into a flock particle. After that, what will happen? We are allowing the water to settle down. Then all your fluorine particles get settled. After that, we are going to filter. After filtration, the water will be sent into your household, like your municipal tank. Okay. First one, flash. So here, flash. We are mixing your. Next one is your rapid mix. Rapid mix is done by using your stirrer. Next one is your flock formation. Next one, sedimentation. The particles gets totally settled here. Next one, filtration. By using the sieve. We are filtering the particles. Now water will be there. Next, this water is sent into the houses. This is how the thing happened. The only chemicals that we are using is lime and alum. That's it. This is about your defluoridation. And it can also be determined by your ionic method. So that means how, like your ADTA method, it can be determined by using the ion method where TSUB is used. So by using the known samples, the unknown sample is calculated. So this is about your defluoridation method. And with this, we completed water technology chapter. Thank you. This is Kundana signing off.
Like, share and subscribe. Hit the bell icon for more updates.